So we're going to learn the current electricity chapter, and you see that I've drawn a conductor, a magnified thin wire, but in a magnified form, so you get an area of cross section, and this is the length L. You have a many number of electrons. You have a many number of electrons here which are randomly moving, and so then when you take a metallic spoon, is it conducting? Which means at room temperature these electrons are moving, which means it contributes to electric current. But we don't feel any current. A normal spoon is not conducting electricity, only when you connect it to the circuit and all that. So then what does it mean? They collide and rebound. So then therefore, supposing the electrons are moving with velocity u1, u2, u3, un charges. Okay, you know that the average thermal velocity, they call thermal velocities, the average thermal velocity is equal to 0. Average thermal velocity, because the initial velocities is u1, u2, u3, but they collide and rebound, and hence the average of it is become 0, and thus a spoon, a normal spoon that you see in the kitchen, is not conducting electricity. Okay, so then but what happens when you connect this metallic wire? So this metallic wire is now connected to an electric field. Okay, you close the key. What happens? These electrons will align itself and start flowing in one particular direction, from negative to positive. You know, the electric current, conventional current flows from positive to negative, but electrons in actual flows from negative to positive. They align itself in one particular direction, and thus constituting to electricity. And can you see that there will be V1, V2, V3 or all the acquired velocities because of the electric field applied. And you know, V1 is equal to U1 plus AT1. They've all been accelerated through an acceleration of A, so V2 is equal to U2 plus AT2. V3 is equal to U3 plus AT3. Vn is equal to Un plus Atn. When you add everything, you get V1 plus V2 plus V3 plus Vn is equal to U1 plus U2 plus U3 plus Un plus A into T1 plus T2 plus T3 Tn. Now divide both sides, left sides, by n. So you're going to divide this by n, divide this by n, divide this by n, so that you get this to be an average thermal velocity. Can you see this is the first equation? By first equation, you get to know that this is equal to 0. So you can call this term as drift velocity Vd plus is equal to and a plus acceleration and a relaxation time t. This whole component is called tau, or relaxation time t. So what defines drift velocity is the velocities acquired by all the electrons when the conductor is connected to an electric field. It's an average velocity. So what is drift velocity? It's an average velocity acquired by all electrons when the conductor is connected to an electric field. So what is this time? This is relaxation time, which is the average time between two successive collisions. It's an average time between two successive collisions. And this is the average thermal velocity, which became 0 from the equation 1, average thermal velocity. So thus you get an equation, Vd is equal to A into T. You know, F is equal to M into A, so A is equal to F by M, and F according to electrostatics is capital E into small e by M. E is equal to F by Q, F is equal to E into Q. So capital E into small e, in the place of charge you can write small e. And so Vd is equal to capital E into small e by M into relaxation time t. You have to include a negative sign here to indicate that the electric field and the drift velocity are opposing each other. The drift velocity, can you see, is from right to left, whereas the electric field is from left to right, positive to negative. So thus the electrons are getting accelerated in a direction opposite to that of the applied electric field. This is one of the most important MCQs. The electrons always gets conclusion from this, accelerated, always gets accelerated in a direction opposite to electric field, opposite to applied electric field, correct? So you know from this. correct? That's the conclusion that we arrive at, and there will be an MCQ based on that. So that's the first derivation of drift velocity. Derivation of drift velocity. Drift velocity is actually drift velocity is capital E into small e by m into relaxation time t with a negative sign, which indicates that E is opposing Vd. Otherwise, when I ask you Vd formula, you can say capital E into small e by m into relaxation time. Okay, capital E is electric field, small e is the charge of electron, m is the mass of the electron, and T is the average time between two successive collisions of electrons, and so this is Vd. You have to memorize this formula. That's the first part of the lesson. Okay, so what is next? Let's derive a relation. So this is drift velocity derivation. Basically what I did now is drift velocity derivation. Now it's all going to be MCQs for you. You just have to know the final velocities formula. Vd is minus capital E small e by m into relaxation time. Now let's arrive at a relationship between current and drift velocity. Current and drift velocity. What is current? Current, you know, I is equal to Q by T. And Q in this conductor, if you see this area of cross section A and this is L, and let N be the number of charges. Let N be the number of charges. Each charge, N is the number of charge per unit volume. Per unit volume. Let E be the actual charge, and the volume is, total volume is A into L, and hence the total charge in this entire volume will be Neal, N-E-A-L, Neal. Charge per unit volume into total charge into volume will give you Neal, Neal. So thus you substitute Q as Neal, Neal by T, and can you see L by T is nothing but velocity. You can call it as NEA, drift velocity. And just for you to recollect, I used to say NAE-VD, NAE-VD, you know. So therefore it's easy for you to recall the formula. So NEA-VD. Okay, so that's about the relationship between current and drift velocity. This is suffix D, okay, this is suffix D. Now I'm going to write, derive Ohm's law from this. Deriving Ohm's law from the above. So you know I is equal to NEA drift velocity, and instead of drift velocity I know I can substitute NEA capital E into small e by m into relaxation time. You can forget about the negative sign. And so you know that basically Ohm's law is V is proportional to I, V is equal to IR at constant temperature. If you don't write at constant temperature, you're going to lose marks. So then the voltage across of a circuit is directly proportional. The current flowing through the circuit is directly proportional to the voltage across the circuit, vice versa. So V is equal to IR at constant temperature is Ohm's law. So I have to arrive at this, using starting with I is equal to NI-VD. VD is capital into small e by m into relaxation time. And I want a V, an introduction of V. I have an I want an introduction of V. So I can write E is equal to V by L, potential gradient. The electric field is nothing but potential gradient, potential by length, V by L. So thus I can introduce a V there, NEA, capital V by L. You have an E here, so you can make it E squared, M and T. Can you see thus you have a V and an I, and you can shift everything to the left hand side but for V, so you get V is equal to IR format. And so I, and you have an L M by N E square A, and 2 here, relaxation time with a V, and this is of the form V is equal to I. So you've shifted it to the left side. This you've shifted it to the left side. So you get it like this. And can you group L by A separately and M by N E square T? Yeah, and this is of the form V is equal to IR. Thus you get an expression for a resistance which is L by A into M by N E square T. And therefore these are constants: the mass of the electron, charge of an electron, number of electrons, relaxation time. So therefore R is proportional to L by A. R is equal to rho into L by A, and this rho itself is this. Can you see? Thus you know that the resistivity is M by N E square T. Just for you to recall, you can even say M by NEAT, NEAT exam, you know, M by NEAT, just to recall, but it's M by NA square T. That is resistivity. And what is resistivity's formula? It's if you cross multiply, you get ohm meter square by meter, so it's ohm meter. Okay, so thus you get an expression for resistivity. You confirm that you got a Ohm's law. You started with I is equal to I Vd, and instead of Vd you wrote capital into small e by m relaxation time t, and you introduced a voltage E is equal to V by L potential gradient, and grouping everything to the left hand side other than V, you get V is equal to IR format. Therefore you know what is R from this, and grouping L by A, you know R is equal to rho into L by A, and so rho is M by NEAT. So this is resistivity, and the reciprocal of resistivity is conductivity, and so the conductivity is Ne square T by M. So thus you know this is conductivity. Okay. So the conductivity will be per ohm per meter, whatever as you say it. Okay, that's about conductivity. Let me derive and now an expression. Okay, now let me tell you what is a current density. Current density is represented by a letter J, which is I by A. One common question wherever the area comes, they'll ask you whether it's vector. Wherever there's area, you know area is normal to the area, and if supposing there's a surface, the area vector is always normal to ds vector is always normal to the ds, and so then therefore area is a vector, and so current density is a vector. The current flowing through unit area. So the definition goes like this: the ratio of current per unit area, or current flowing through unit area. So then SI unit is ampere per meter square. This is current density. But you know that current density I by A, instead of I, you can write I with NEAVD by A. So A and A get cancelled, which will result in NEVD. And VD itself, you know, is drift velocity suffix, which is capital E and small e by m into relaxation time t. And so the current density J is equal to NE square T by m into capital E. I'm just rearranging them. And can you see that electric field is a vector, current density is a vector, and this is nothing but the reciprocal of resistivity M by NEAT. It's conductivity, so J vector is equal to conductivity times electric field, and this relationship between the current density, the relation between current density and electric field is very important, is very, very important. Okay, so you should know this. If you know the electric field and the current density, you can find the conductivity of the metal, and hence you can find the resistivity. Okay, so that's the current density topic. So after this, after current density, I would do, we'll talk about Ohm's law, limitations of Ohm's law, because we have dealt with Ohm's law now. So now that we have dealt with Ohm's law, let's do the limitations of Ohm's law. What are the limitations of Ohm's law? Okay. So the first limitation of Ohm's law is about the copper wire. You know that this is a graph between I and V. You know, it's supposed to be for a metal like copper. It's supposed to be a straight line, a linear equation. You know, V is proportional to I, V is equal to IR according to Ohm's law, shows that it's a linear at constant temperature, shows that it has to be linear relationship. But actually, beyond a particular temperature, the conductor is actually getting heated up. The conductor is getting heated up and it will become non-linear. Okay, one second, it will become non-linear. Let me take that. So therefore, it's going to become non-linear, and that is a limitation of Ohm's law. It's not obeying Ohm's law, because as per Ohm's law, it has to be a straight line. And so beyond a particular value of current, it is not obeying Ohm's law. It is turning from linear to non-linear. Okay, that is the first graph of limitations of Ohm's law. Okay. So how is it going to go? It's going to go like this. Instead of straight line, it's going to turn around like this. It's non-linear. If you had done a VI graph, then in that case it would go like this, you know. So you should be careful about whether you're doing IV or a VI, and based on that you should do the limitation of copper, the first limitation. The second limitation, that is, you know why this limitation is happening? Beyond a particular value of current, the conductor is getting heated up, and so it's not obeying Ohm's law. Okay, so then that's the first point. The second point is about PN junction diode. PN junction diode is a diode is like this. Okay, this is a diode. Actually, it will look like this. It will look like this. It will have a positive terminal and a negative terminal, and a diode is represented by a triangle like this. This triangle represents the positive side, and this represents negative terminal. So this is a diode. It's a semiconductor. PN junction diode is a semiconductor device. A conductor, a non-conductor, and in between them will be a semiconductor. Okay, so semiconductor device. And supposing you're going to forward bias this. What is forward biasing? Is to connect the positive of the diode, which is the triangle is the positive, to the positive terminal of the battery, and the negative to the negative. And this is called forward bias mode. Forward bias mode. And supposing I'm going to connect like this, which means a positive of the diode is connected to the negative of the battery. It's called reverse bias mode. Reverse bias mode. And for this, the graph will be, this is voltage plus V and minus V. This is for forward bias, and this is for reverse bias. Reverse bias and reverse voltage and forward voltage basically. And the current is I and minus I. You know, the graph will go on like this, like it will be like this. And here it will be very, very close to the x-axis. And at one point, it will start rising steeply. This is a very, very important graph, and can you see it does not completely obey Ohm's law, be it in the first quadrant or in the third quadrant. It is not obeying Ohm's law, and this, in this case, the current is actually, the reverse bias mode is microamps, in the forward bias mode is milliamps. And when you do a forward bias, you get more current, a little more current when compared to reverse bias. Okay. So that's the second limitation of Ohm's law, which is not obeying Ohm's law. That is a PN junction diode. Then is a thyristor. What is a thyristor? Thyristor is actually 4 alternate layers of PN junction. At the PN junction, you have 4 alternate layers, okay? 4 layers of a PN junction diode. So it's a 4-layer PN junction diode, alternate layer of PN junction, okay? So that's called a thyristor. That's again a semiconductor device, again a semiconductor. You know, how is the graph going to be for this, for a thyristor? You, you notice that you commonly put an IV graph, you don't put a VI graph, okay? The common thing is to put a IV graph, but if you put, you have to bring it down like this, okay? It's all IV graphs that I'm continuously doing. This is I and this is V and this is minus V and this is minus I, and it's forward bias and reverse bias because semiconductor is there. And thyristor is nothing but a PN junction, 4-layered PN junction diode alternative. So then the graph goes like this, you know, the first quadrant. And here it's the same, it goes like this and steep like this. So then there's no change in the third quadrant as such. But in the first quadrant it's like this. It shows that, you know, for one particular voltage, you have 2 different values of current. Current value is not unique. Current value is not unique. You know, that's, it cannot be, that's not Ohm's law. That's not what Ohm's law says. So let's go to next 4th limitation, is gallium arsenide. So let's look at gallium arsenide. Gallium arsenide is again a semiconductor. Gallium and arsenic together, it's an alloy. It behaves like a semiconductor. Okay, again a semiconductor. So in that, let's see how the graph is. IV graph. I always put an IV graph. I prefer that for consistency. The graph goes like this and comes down like this. Can you see that? Therefore, you have 2 different voltages for one particular value of current. So voltage is not unique. Voltage is not unique. So these are all what you have to write for limitations of Ohm's law if they ask you detailed answer. And just for you to know, there's one more point. What is superconductivity? Superconductivity is like a conductor becomes a superconductor. It allows infinite current to pass through. It's a superconductor. So like you can make a conductor become a superconductor say certain material, only certain material, okay, like certain metals such as mercury. You can choose mercury as an example, and you have to lower the temperature, and at 4 Kelvin, it's behaving like a superconductor. So this is about it is about the y-axis having a resistance in ohms. It loses all its resistance. Can you see? And this is temperature in Kelvin. At 4 Kelvin, when you reduce the temperature, the conductor loses all its resistance. Resistance gets to x-axis, and it behaves like a superconductor. And okay, that should be sufficient. And how is it possible for superconductivity? In case there's an MCQ on it, when you lower the temperature, actually when you have an electron and an electron, it's supposed to be repelling each other, right? Because of like charges. But when you lower the temperature, it actually gets a weak attractive force acts on the electrons. That gets a weak attractive force when you lower the temperature. This weak attractive force between the electrons form a coupled electron pair, and this electron pair will flow through the conductor without getting collided with the ion. Actually, let me talk about resistivity and the resistance. How is that a metal is having resistance? What brings in the property of resistance? You have a metallic conductor in which there are so many atoms, and every atom has got free electrons in its outermost shell. It is these free electrons which tends to move. And when they move, they can collide. When they move, they leave behind a positive ion in that particular atom. Say an electron leaves a positive ion. So these electrons can collide with the adjacent positive ions of the metal. And that is what is causing the resistance. So what is responsible for resistance is the electrons collision with the positive ions. And that's what gives rise to the resistance. Whereas this electron pair here does not get collided with the positive ions. Because they form an electron pair, the adjacent there is no positive ion and there is less positive ions, and they manage to move without much collision. So then it gets to superconductivity. It's not going to be asked, it's only for your knowledge. But this is very important. What causes the resistance is the collision of electrons with the positive ions. Okay, then let me talk about Meissner effect. That's again only for knowledge, and if in case there's MCQ is going to be asked, what is Meissner effect? You're going to place a metal and lower the temperature. So you're going to take a conductor and cool the temperature, and also simultaneously you're placing it in a magnetic field. You're placing it in a uniform magnetic field and also lowering the temperature. At a temperature which is lower than the critical temperature, the magnetic field lines will get diverged like this. Okay, this phenomenon of pushing of the magnet, pushed out. Can you see the magnetic field lines get pushed out? And this phenomenon is known as Meissner effect. So it's called expulsion of magnetic field lines. It's called expulsion of magnetic field lines. And this is known as Meissner effect. The Meissner effect indicates that as you're placing a superconductor, right? You're placing a superconductor. How do you get a superconductor? By reducing the temperature. For example, mercury is 4 degrees Celsius, and you're placing it simultaneously in a magnetic field. And at that time, at a particular temperature, the magnetic field lines get expelled, the expulsions of magnetic field, and it behaves like perfectly diamagnetic substance. This substance behaves like a diamagnetic substance. The material can be classified into dia, para and ferro depending on how the magnetic field lines are going. So the diamagnetic substance always expel the magnetic field. Whereas a paramagnetic, a few lines will go in the magnetic field. In a ferromagnetic, lots and lots of field lines will go through the ion, a ferromagnetic substance. So then we don't need that, and that portions has been deleted, so just this is enough. So then is about Resistance in parallel, resistance in series, you know, you've done it in 10th standard, so I'm not going to do that part again. So next is carbon resistors. I'm going to talk about carbon resistors. It goes like this. It's B.B. Roy, Great Britain, very good wife. So it's black, brown, this is blue. Okay, this black and we can get mixed up because alphabetical order, but blue is coming here. This is red, orange. It's not in alphabetical order when it comes to brown and blue. Just have to remember that. This is yellow, green, violet, grey, and white. So B.B. Roy, Great Britain, very good wife. And then gold, silver, and platinum. Gold, silver, platinum. So the numbers have to be given like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this will be plus or minus 5% for the error, plus or minus 10%, plus or minus 20% for the error. This is the error part. Okay. Okay, 1 second, hold on. So that's for B.B. Roy, Great Britain, very good wife, which is about the carbon resistors. So let me do a carbon resistor, an example for you, because that's an important question which keeps coming in the exam. Okay. So supposing you have a carbon resistor like this, it's a very tiny resistor available in your lab. Supposing you have two red colors, you have a red color and a red color, and then an yellow color, and a platinum, say, or a gold color, or a silver color. Okay, let me do a silver. This is easy. Let me consider that this is silver. Okay. So what is it as gold? Red color stands for 2. Another red color stands for 2. So 22 from this. Into the third color stands for 10 to the power. 10 to the power yellow is 4. And silver stands for the error, which is plus or minus 10%. So this is how we identify the value of carbon resistors. Okay. Let me figure out some more examples of this. Give me 1 second. No, it's not internet. So this is about it. So B.B. Roy, Great Britain, very good wife is something you got to remember. 5%, 10%, and 20% are the errors. So plus or minus you have to specify. So I'm sure everybody understood this. And if I have to give a few more examples. We can have an yellow first, a violet next, a brown next. Where is brown? I don't have a brown color, so let me do it. Let me do this and do a red over it to show that this is brown. It's not coming. Say it's brown. Okay. Sorry, brown color, and then a gold color, and then a gold color, gold. So how am I going to write? Yellow stands for 4. The next purple is violet, which stands for 7, 47. Into 10 to the power brown. What is brown stands for? It's 10 to the power 1. Plus or minus what is gold stands for 10%. So it's 47. Okay, so this is the way you have 47 and 10 to the power 1. And the SI unit will be ohms because you're writing the resistance. So this is how you identify the carbon resistors value. So it's important to remember B.B. Roy, Great Britain, very good wife. After which I have to teach you next topic is the most important topic, which is the coefficient of resistance. So temperature coefficient of resistance. Okay, as you know that as temperature increases, the resistance increases, right? Because it's given by formula R is equal to R naught into 1 plus alpha T plus beta T square. Can you see a quadratic equation T square and T shows that it's parabolic, As the temperature increases, the resistance increases. It's not though linearly, it's not linear. Can you see it's parabolic? Yeah. But however, where this T is actually a small change in temperature, it's delta T. Okay, for a change in temperature, there's a change in the resistance and it increases. So when I say delta T the whole square, it's a fraction of temperature when squared can become negligible, so I can ignore. So which leaves me behind with R is equal to R naught into 1 plus alpha T, where alpha is a coefficient. Can you see temperature coefficient? Yeah, that's why it's called temperature coefficient of resistance. And so let's take R naught inside. R is equal to R naught plus R naught alpha T. Thus alpha itself is R minus R naught by R naught into T, which is change in the resistance to original resistance per degree rise in temperature. Change in the resistance to original resistance per degree rise in temperature. Resistance, ohm and ohm get cancelled, so per degree Celsius. That's all, per degree Kelvin. That's what is coefficient of resistivity. And same thing stands for temperature coefficient of resistance too. Supposing the question is about temperature coefficient of resistance, of resistivity. The same equation, rho is equal to rho naught into 1 plus alpha T plus beta T square, and you continue and write alpha to be rho minus rho naught by rho naught into T, which is change in resistivity to original resistivity per degree rise in temperature. So the same derivation applies for this, whatever you did here. So this is about the alpha, therefore is called the temperature coefficient. Okay, alpha is called the temperature coefficient. Okay, so next thing that I've got to teach is I think I'm almost done with the introduction part. This is all is for the introduction. Okay, so okay, where is it? Where is what I wrote? Okay, it's missing, but you'll have it in the video, I guess. If something is not all right, it's got deleted. But you have the lesson actually is going to begin only here. Okay, so you know about resistance series and resistance in parallel and stuff. Now let's talk about batteries. Okay, supposing you go and purchase a battery. Okay, you go and purchase a battery. This is the second part of the lesson. Okay, it will say, supposing you're buying a 2-volt battery, that is called an EMF. EMF of the battery, which is electromotive force. Say it's a 2-volt battery that you're buying, it's electromotive force. When no current is flowing through, when you're buying it from the shop, no current is flowing through, right? It's just a battery. So then electromotive force is the potential difference between the ends of the electrodes when no current flows through. When no current flows, that is known as electromotive force, EMF. What happens to this battery? This is a 2-volt battery, and you are representing this as E, capital E, which is the electromotive EMF. We'll call it as EMF. Okay, EMF. That's called an EMF, which is the potential difference between the two ends of the electrodes of the battery when no current is flowing through. The moment you connect this battery to a circuit and allow a bulb to glow, which is a resistance, which has got high resistance, right? That is external resistor and a switch. Suppose you close the switch and key is closed and current is allowed, and you connect a voltmeter in parallel and note on the reading of the voltage. It will not show 2 volts, it will probably show 1.6 volts or 1.8 volts. So will you go back to the shopkeeper and say, what is this? I bought a 2-volt battery, it's showing only 1.5. You can't do that. Why? You know, when actual current starts flowing, when the current starts flowing, the internal resistance of the battery comes into play. Every battery has an internal resistance because there is this chemicals inside, and the ions of the chemicals, will collide with each other and offer resistance, and so there is an internal resistance, which is small r, internal resistance, which is small r. And this voltage that is shown in the battery is called terminal potential difference. Terminal potential difference, V. So what is E? The voltage that is shown in the battery when you're purchasing, but that's when no current is flowing through. What is V? It's terminal potential difference, which is the potential difference between two terminals when current is flowing. When current flows, you know that V will be lesser than E. The reading in the voltmeter will be lesser, and therefore, and R is the internal resistance. When the current starts flowing, the internal resistance crops up. In the chemicals, it's providing resistance, ions in the chemicals inside the battery. That is showing its head, and so the relationship between V and E is V is equal to E minus IR. Can you see? This is a very, very important relation. V is equal to E minus IR. You know, V is less than E. And how is it? The relationship because of the internal resistance and the current flowing through. That's what is attributing to the reduction in the voltage. And so V is equal to E minus IR. And also, you should know that I is equal to E by capital R plus small r. The total resistance is the internal resistance plus capital R. So total resistance therefore is capital R plus small r because they are both in series. And so at any point of time, this is E. You have to remember these two equations which forms the crux of this entire, the fundamental of this entire lesson is this. The terminologies such as what is E is the EMF when no current is flowing through the battery, terminal potential difference when the current is flowing through, and the internal resistance crops up when the current flows through. And the two main equations, V is equal to E minus IR and I is equal to E by capital R plus small r, is very, very important. This forms the basis of this lesson. So we can substitute this I in this equation. So V is equal to E minus E by capital R plus small r into R, where I am going to cross multiply VR plus V small r is equal to E capital R plus E small r minus E small r. This and this get cancelled. I want to find a relationship between capital R and small r. So I'm going to consolidate capital R. So then I'm going to take this that side to the other side. So VR is equal to ER minus VR. So R into E minus V. So small r is equal to capital R into E by V by E minus V by V. Small r is equal to capital R into E by V minus 1. A very, very important final formula that you've got to remember. Internal resistance of the battery will be equal to the external resistance times E by V minus 1. What is E? EMF of the battery. What is V? The terminal potential difference minus 1. So this formula again is very, very important. So if you want to recall, you know that the total charge in a conductor is Nial. Then drift velocity is capital E into small e by m into relaxation time t with a negative sign, of course. And we can forget about the negative sign if you're writing only the formula. Then I is equal to NE ABD NIBD. And J is equal to I by A. And J is also sigma times electric field. So, you know that resistivity is M by neat, Ne square T. Conductivity is Ne square T by M. So, supposing you want to find resistance, rho into L by A. So, simply by multiplying ML by Ne square T into A, you get in L and A, you can change it into resistance. So, thus at any point of time, you want to know the formulas, you can quickly recall. And now comes a relationship between small r and capital R. So small r is equal to capital R into E by V minus 1, where R is external resistance and small r is the internal resistance. So this derivation is very important because we'll apply it in sums, or the derivation may be asked. It's a relation between internal resistance and the external resistance. Smaller, very, very important. We'll apply this in potentiometer in a later date, so later time. So it's very, very important. Okay. After this, I'm going to talk about what happens if, say, a number of batteries are connected together. Okay. So, for which let me see. Let's do this graph for this particular thing that I've written here. Okay, let's see. V is equal to E minus IR. The graph will be like this, a V on the y-axis and an I on the x-axis, and V on the y-axis, I on the x-axis gives you a slope, and the slope is minus R. It's a negative slope. Anything like this is negative, anything like this is positive slope, so then therefore it's a negative slope. And you know it's minus IR, you know, V is equal to E minus IR. So obviously this R is here is negative, so negative slope. And this graph is very important. What can you infer from this graph is when, can you see when there's no current, when there's no current, that's current is 0, V becomes equal to E. Whatever was shown in the battery, if it's 2 volts, it's 2 volts. You know, when the current starts flowing, when the current actually starts flowing, can you see the voltage goes on getting reduced? So that's the relationship as to how you have to draw. Okay, next is about a number of batteries connected together. Say supposing you have a battery here, like this, a number of batteries, all of which are connected together. You should know a simple thing that I want to tell you is when a battery is connected like this, it's E1 and E2, it's E1 plus E2, okay? When a battery is connected like this, that's negative is connected to negative, it's E1 minus E2. The simple thing that you've got to remember here is this. Okay, now let's continue with it. The number of batteries are connected together in series. And similarly, you also have these batteries in parallel. And it goes on like that. A number of cells are connected, okay? So then it goes on like this. There are many rows and columns. So let's consider that there are n cells, 1, 2, 3, 4, 5, n cells. And each of EM of E, and it's got internal resistance. Everything has got internal resistance. Let's keep it as uniform small r. Okay, and if the batteries are uniform E, then the total EMF is N into E for this particular row, and the total resistance is NR because they're all in series. And then the number of, this way when you count, there are M numbers of lines, and so then therefore if I have to calculate the equivalent resistance, it will be 1 by NR. For one row it's NR, so next row it's NR, so 1 by NR plus 1 by NR plus 1 by NR plus dot 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 1 by NR. When you take LCM, because they are parallel, correct, it will be M by NR, M by NR, because there are M number of lines, so then this is a resistance in parallel, is a equivalent resistance in parallel, and therefore RP is NR by M. The equivalent resistance, internal resistance, the equivalent internal resistance. Suppose this entire setup is connected to an external resistor, capital R, and then a key, and you know it's getting close like that. Can you imagine? Yeah. In that case, the total resistance is capital R plus small r. So capital R plus RP is the total resistance, which is capital R plus NR by M. This will be the total resistance of the entire circuit. And you know that the current I is generally E by capital R plus small r. But in this, every row has got N batteries, N cells, so NE by capital R plus RP. So which is going to become NE by capital R plus NR by M. So when you take LCM, you will get MNE by MR plus NR. So this is the value of the current that you get that is flowing through the circuit. And for this current to be maximum, this denominator has to be minimum. The denominator has to be minimum. So for this to be minimum, let us see how we can make it minimum. Let's write MR plus NR as root of MR whole square plus root of NR the whole square, which is just nothing but the same, right? The root and square get cancelled, it leaves you to MR plus NR only. So we're purposely writing like this so that it's like of the form A square plus B square, which can be written as A minus B the whole square plus 2AB, you know. So this will be root of MR minus root of NR the small r the whole square plus 2 times root MR root NR. So if this has got to be minimum, can you see this can become 0? So then the condition for the current to be maximum is the denominator to be minimum. For the denominator to be minimum, this component has to be 0. So MR is equal to NR, or the external resistance is NR by M. The value of the external resistance can be equivalent to the internal total internal resistance, equivalent internal resistance NR by M. So by connecting an external resistor which is equal to the equivalent internal resistance NR by M, you can make sure that you get a maximum current in the circuit. So they might ask you this in numericals, and you should know that capital R is NR by M. And so that's another formula that's been added. Okay, so next topic. It's such a huge lesson. It's such a huge lesson when there is the heating effect of electric current. Only the heating effect of electric current, I'll put that in a separate video, or I'll teach you in a class when we are learning in the class. So let me do what is Kirchhoff's law. Kirchhoff's law. It consists of a junction rule and loop rule. Okay, this consists of a junction rule. The next one is a loop rule. What is a junction rule? Supposing there's a junction here. This is I1, this is I2, current flowing towards the junction, I3 and I4, current flowing away from the junction. The sign convention is current flowing towards the junction is taken as positive, current flowing away is taken as negative. So, and the sum of the current flowing through the junction is always 0. That is, sum of the current flowing towards the junction is I1 plus I2 positive, away from the junction is minus I3 minus I4 is equal to 0. So, I1 plus I2 is equal to I3 plus I4. That is, current flowing towards the junction is equal to current flowing away from the junction, or the net current flowing into any junction is always equal to 0. That's the junction rule. What is a loop rule? You have to remember what I'm drawing here for a loop rule. You have a battery here and a resistor here and only a resistor here and a battery here and a resistor here. Let's have this as a fixed diagram to prove a loop rule. Supposing this current I1 which is flowing like this, and this is a current I2 which is flowing like this and through this junction, therefore it has to be I1 plus I2 which is flowing away from junction. Current flowing towards should be equal to current flowing away. We can call it as I3, but I3 is anyway I1 plus I2. Let's name this as R1, this resistor is R2, this resistor is R3. And let's name this battery as the cells as E1 and E2. Let's name the cells as E1 and E2. Okay, now let me name this as A, B, C, D, E, F. I'm not sure if you had learned this loop rule. It's very, very important for us to be able to solve any problem. Supposing you're going to take a closed loop, a closed loop A, B, C, D, A, which is an anti-clockwise direction. This direction which I'm going, A, B, C, D, A. The closed loop, the loop rule says that some of the EMFs, some of the potential and the products of the current and resistance, which is also the potential, is always equal to 0. Sum of all the potential is equal to 0. So that's the loop rule. So around any closed loop of network, the algebraic sum of the changes in the potential must be 0. The algebraic sum of the changes in the potential must be 0. Or you can say the algebraic sum of the EMFs in any loop of circuit is equal to the sum of the products of the currents and resistance. Algebraic sum of the EMFs, that is E1 plus E2, is equal to the sum of the products of the currents and resistance. Or we can say in simple terms, the algebraic sum of EMFs and the products of current and resistance. Current and resistance products is nothing but voltage, right? Current and resistance is always equal to 0. So let me apply that here. So I'm going to go from A. So look at the way I'm going from A. Yeah, I have a battery which is going from positive to negative. When it's going from positive to negative, it's minus E2. The sign convention for a battery is when you go, it's from positive to negative, it's minus E2. Okay, so then you go further in the same direction. You have an R3 in which the current is flowing in the opposite direction. When the current flows in the opposite direction, it's plus I2 R3. If it's in the same direction, it's minus. It's in opposite direction, it's plus. So the direction which I am going, the current is going in the opposite direction. So plus I2 R3. The I2 is the current that flows through this wing. Okay, so then go here, and you have resistance which is the resistance R2, in which the current is flowing in the opposite direction again. To the direction which I am going, current is flowing in the opposite direction. So plus I1 plus I2 into R2 is equal to 0, and it's closed. So this is how we write a loop rule. So let's go to next circuit. Let's go to the closed loop DCFED, and let's consider anticlockwise direction in which I am going to go. I'm starting from D, yes, I'm starting like this, and I'm going like this, and I have a resistor R2, which is the same direction. The current is flowing in the same direction. So minus I1 plus I2 into R2, and go on. It's going the same direction. It has to be negative, okay. And there is R1 in which the current I1 is flowing, and again it's flowing the same direction in which I'm going. So minus I1 R1. The battery is negative to positive, so plus E1, and the getting close is equal to 0. So that's this is how we write the loop rule, and we look at the directions. Okay. So next is Wheatstone's bridge. So numerous sums are there in this. It will at least take 2 classes or 2 classes for me to complete all these numericals. So let's look at a Wheatstone's bridge. Wheatstone's bridge. What is a Wheatstone's bridge? It will have a resistor here, a resistor here, a resistor here, and a resistor here, and a galvanometer here. Let's call this as PQRS. Connect this to the external circuit. You have a battery and a key. The key can be closed, and supposing there's a current I which is getting in. If this is I1, this will be I minus I1, correct? And since this is IG, this will be I1 minus IG. And what is going to come out from this will be both this current that is coming from here and this current, which is IG. So it's I minus I1 plus IG. And when it comes out, it will come out as I, because I1 and IG will get cancelled from here and come out as I. So this is the diagram for a Wheatstone's bridge. So you are going to name it. Let's name this as A, B, C, D, and this is based on junction rule and loop rule. The fact that there's I1 and I minus I1 is flowing here shows that junction rule is being applied. I also have to, so there's junction rule and loop rule. The principle of this is junction rule plus loop rule. So how am I going to apply the loop rule? Let's see, let's take this anticlockwise direction, which is A, B, D, A, A, B, D, A. So I'm going to apply loop rule in this. So you know how to apply loop rule. Just draw from here. A, there's a resistor in which current is flowing the same direction. So it's minus I minus I1, minus of, into R, resistance R. Go like this, in the same direction. There's a galvanometer's resistance is G, and the current is flowing in the opposite direction. So plus IG into G. Current is flowing in opposite direction. So plus. And go to this resistance here. The current is flowing in opposite direction. Plus I1 into P is equal to 0. This completes the first loop. So let's go to the second loop, okay, which is B, C, D, B. Let me do it in different colors so that you're clear. So it's B, C, D, B. And I'm going to start from B. I'm going anti-clockwise again. The direction, the current is flowing the same direction as me. I'm going, so that's got to be negative. So minus of I minus I1 plus IG into S, that resistance. and this resistance Q here where the current is flowing in the opposite direction, plus I1 minus Ig, plus I1 minus Ig, plus I1 minus Ig into Q. So complete. Ig is flowing the same direction. So minus Ig into G. So minus Ig into G will be equal to 0. That's all, it's closed. Now you write these two equations and now consider, assume that Ig is equal to 0. The current flowing through the galvanometer is 0. There is no current flowing through the galvanometer. So mark this Ig becomes 0, this Ig becomes 0, this Ig becomes 0, this Ig becomes 0. So what happens to these two equations is going to get converted into I minus I1 into R is equal to minus I1 into P. Taking this, that's it, because Ig has become 0, this becomes 0. Similarly, I minus I1 into S, because this Ig has become 0, is equal to minus I1 minus Ig into Q, because this has become 0. I minus Ig again is 0, sorry. So I1 into Q, I1 into Q. So now you can divide these two equations. The negative anyway gets cancelled. You can divide these two equations, and this and this get cancelled, this and this get cancelled. You get R by S is equal to P by Q, which is a very important conclusion. This is a balanced, it's balanced bridge, you know. The resistors are having the same or in the same proportion. P by Q, this P by this Q is equal to R by S, or P by R. You can even write P by R, bring the R down and taking the Q to the top, Q by S. So therefore you conclude that we assume that when the galvanometer current is 0, then the resistors or the ratios of the resistors are proportional. Which means the ratios of the resistors are proportional, then the galvanometer will show 0 deflection. No current will flow through galvanometer. The converse is true. Okay. So that's what is all about Wheatstone's bridge. Then is meter bridge and potentiometer. Next is meter bridge and potentiometer. Okay. See, meter bridge basically works on the principle of meter bridge based on the above principle, which is Wheatstone's bridge. This principle of meter bridge is Wheatstone's bridge, the balanced bridge, you know, when the resistors are balanced at the right proportion and no current will flow through galvanometer. So Wheatstone's bridge principle. Wheatstone's bridge is the principle of meter bridge. Sorry about my bad handwriting, I have to rush it through because you need it for exam. So basically a meter bridge consists of two copper strips, L-shaped copper strips, and a straight copper strip, and with the gap G1 and G2, the two gaps G1 and G2. Okay, and there are terminals here, and also in the middle. You can connect a known resistor, resistance box here, a known resistor, and an unknown resistor X, an unknown resistor X here. This is a known resistance R, and you have a meter bridge has a meter wire, at 1 meter wire, which is connected to this copper strip, from which there is a battery key. You can have a battery key. You can also have, nothing wrong, a variable resistor here and close the circuit. From the central terminal, you know, from here, you have to have a galvanometer and a jockey. So this is the diagram for a meter bridge. So this is L-shaped copper strips, L-shaped copper strips. Okay, and these known resistor. So you will have a length here L, and this will become 100 minus L, because it's a meter wire. 1 meter wire, 100 centimeters. So in terms of centimeter, if this is L, that is 100 minus L. And you know, resistance is directly proportional to L. Resistance is directly proportional to L by A. The area of cross section is a uniform wire. It's a uniform cross section area wire. Okay, of uniform constitution. Uniform constitution. Say if it's manganese, it's manganese throughout. It's constant throughout, like that. Uniform composition and uniform area of cross section, composition, constitution. Okay. So R is proportional to L by A. A is the same throughout. Whether it's this side of the wire or that side of the wire, area of cross section is the same. So only the length is going to change. And supposing this is like R and X, and this is like P and Q are the resistors. Suppose I'm going to call it as P, and let P and Q be the resistance of these wires on the left and the right. In resistance, the resistance of P will be proportional to L by A, and the resistance of Q will be proportional to 100 minus L by A, and so then our P by Q at any point of time will just be proportional to L by 100 minus L, because A and A get cancelled. P by Q is just this is the ratio of P by Q, and there is always rho, but rho will get obviously cancelled, right? If you put equal to, you will have a rho into L by A, and the rho and rho will also get cancelled. So then you don't have to worry about rho, and you can just write it as the ratio P by Q is equal to L by 100 minus L. And at some situation we are considering that the galvanometer here is showing zero deflection, which means no current is flowing through the galvanometer, at which case you can say that this resistance are all in proportion according to Wheatstone's bridge. So you know that it's R by X is equal to L by 100 minus L. So if you have an unknown resistance, you can reciprocal this. X by R is equal to 100 minus L by L, and thus you can find the value of X, which is 100 minus L by L into R. Thus you can find the unknown resistance, and the Wheatstone's bridge is used to find the unknown resistance. Even this can Wheatstone's bridge, a meter bridge. Both of them are used to measure. If you don't know any of the resistances in this case also, you can use even a Wheatstone's bridge or a meter bridge to find the unknown resistance. Okay, and so that's based on the principle of Wheatstone's bridge. Next is potentiometer. There are numerous sums and conceptuals. So unless you clear with the lesson itself, it's going to be very difficult for me to teach the conceptuals. I'll do the conceptuals in a separate video, or I'll try to teach you on Thursday. For now, learn from here. Let's do potentiometer. Potentiometer. The principle is suppose a constant low current flows through. A constant low current flows through. The potential drop across any length of the wire is proportional to the length of the wire itself. The potential drop across is proportional to the length of the wire. That is, V is proportional to L. The potential drop across any length of the wire is proportional to L. So therefore, V is equal to K into L, where K is a proportionality which is V by L, which is potential gradient. Can you see? So K is nothing but the potential gradient. Potential gradient. So this is the principle of the potentiometer. Potentiometer is called an ideal voltmeter. Ideal voltmeter. Voltmeter is used to measure voltage. We always connect it in parallel, right? But still it has got some inbuilt resistance. Whereas in potentiometer, we are working on, it's similar to this, we'll be working on zero current. We'll be working on, the galvanometer will show no deflection, zero current through the circuit. Since we are working on zero current in the circuit, no resistance will even come into play. Absolutely no resistance will come into play. And so we get a more accurate value. So that is why it's called an ideal voltmeter. A potentiometer is called an ideal voltmeter. So again, it's zero current. So let's see what is the construction and working of potentiometer. Okay. Basically, potentiometer has got 4 to 10 meter long wire. In the meter bridge, you had just 1 meter wire. Here you can have 4 to 10 meter wire. And how is that going to be? Let's see, a 1 meter wire like this, another 1 meter wire goes like this, okay, and you will have a copper strip here. So this two connected, interconnected. Then another 1 meter wire goes like this in a copper strip here. A 1 meter wire goes like this in a copper strip here. A 1 meter wire goes like this in a copper strip here. So like that you have 1, 2, 3, 4, and you may have even continue to have even 10 meter wire. So then this is how it goes, and this wire is made up of uniform native cross section. It can be Constantan or manganin. This wire can be Constantan or manganin, uniform composition, and uniform cross section area, and each 1 meter is each 1 meter. Can you see, each 1 meter is mounted on the wooden board parallel to each other, and these ends of the wire are connected by means of copper strips, thick copper strips. Okay, and there will be a meter scale which is also mounted on the wooden board in order for us to note down the reading as we measure. Okay, so I measure the length. There it was just L and 100 minus L. There will be a scale there, so you can directly measure the length and 100 minus L. Here also there will be a meter scale. And the first wire, when you do go along this, it will be 100 centimeter, then it will be 150, supposing it's here, and it continues like that. Okay, that's how we measure. And so let's come back to the original diagram. I just want to put one wire here, which shows that there are actually 4 parallel wires or 10 parallel wires of 1 meter long, to make it simple. And what comes in the bottom here is going to come in the top here in this case. So you will have a battery, you'll have a key, and you'll have a variable rheostat, and a 10 meter wire. This is a 10 meter wire. Can you imagine? It's not just 1 meter, but it is. I can't do that. I'm not good at drawing, but this is how it goes, and this is the construction you have here. So you have a battery, key, rheostat, and you can here have a battery here, and another battery here, a key here, another key here. If one is closed, other has to be open. You can have a galvanometer, a high resistance box, and a jockey. Even in this, there was a jockey. The jockey is like a metallic pen which we place on the length of the wire, length of this 100 meter wire, to find where is it balancing. That is when there is no current through the galvanometer. Galvanometer is showing no deflection, So you have a setup like this in this case. So you have this is the original aim of the battery. This is 2 voltages. We're going to compare 2 EMF of the battery. Supposing you want to compare 2 EMFs, and this is E1 and this is E2. There's a K1 and there's a K1 and there's a K2. You know what? As we run through this jockey on the metallic wire at some particular length, the galvanometer will show 0 deflection. For some particular length, you can measure the length. So initially, we'll keep the K1 closed and K2 open, so that E1 is connected to this is called a driver circuit or auxiliary circuit. Driver circuit or auxiliary circuit. And this is called a secondary circuit. Okay, secondary circuit. And if there is no current through the galvanometer, which means there should be no current flowing from the circuit, which means this battery and the battery E1 should be at the same potential. So that normally we choose batteries with, if this is a 4 volts, this has to be 2 volts. It can't be, so that this 4 volts can drop down to 2 and become equal, and thus E can be equal to E1. E can become equal to E1. Similarly, in next case, when K2 is connected, E can drop down to E2. So the potential drops. Can you see? The potential drops from 4 volts to 2 volts. So that therefore it's mandatory that the auxiliary or the driver circuit voltage is always higher than the batteries in the secondary circuit. because the voltage has dropped down and become equal, so when there's no potential difference, there no current will flow through, and so the galvanometer will show zero deflection for one particular length. So I'm just moving and saying at what instant this happens, so that I can note down the length. And now this E1, I told you that the potential drop across any length of the wire is directly proportional to the length of the wire. So then here the potential has dropped from E to E1, and this E1 is proportional to L1, which is the initial length that I'm measuring when there's zero reflection. So E1 is equal to K into L1. Next I'm keeping K1 closed and K1 open and K2 closed, in which I'll get another length L2. And that case that E will drop down to E2. Correct? And so then in that case E2 is proportional to L2. E2 is equal to K into L2, where K is the potential gradient. And E1 by E2 therefore is K L1 by K L2. K and K get cancelled. Thus, by knowing the two different lengths, we can compare the two EMFs. So the first purpose of a potentiometer is to compare two unknown EMFs. You have two batteries, you don't know what their EMFs are, you want to compare them, this is the way you compare. So that is the purpose of a potentiometer. So the main points that they'll ask you in this potentiometer, why is that the auxiliary circuit's voltage has to be greater than the secondary circuit? Because it has to drop down, and that's when no current will flow from. Initially this is at a higher potential, this is at a lower potential, the current keeps flowing. That stops when it drops down and becomes E1 or E2. And this potential drop is proportional to L1 and L2, and so then you get this. So it's mandatory for the potential to be of the auxiliary circuit to be more. What is the purpose of a high resistance box here? Next question. The high resistance box prevents the galvanometer from getting heated up. So that's the purpose of having a high resistance box. So that completes one application of potentiometer. The second application of potentiometer, this can also be used to find an unknown EMF, the same thing. If you know E1, you don't know E2, you know L1 and L2, so you can find what is E1, So then it's also used to find an unknown EMF, compare two EMFs, find unknown EMFs, then and that too with the most accuracy, because it works for no current mode. It's called an ideal voltmeter. Okay. So the next application, it's the last application. The battery has to be drawn up. It's a driver circuit's battery, and there will be a key and a rheostat always on the top here. You have a 10-meter wire or 4 to 10 meter wire which is running here, and you're going to find an internal resistance of a battery. You have a battery here, you have a cell here, you want to find internal resistance, small r. This is capital E, this is V. Okay, or you can even call this as E1 initially, E1, and you have to have an external resistors, capital R here, a key here, and then close the circuit and take it to a galvanometer, a high resistance box, and a jockey. This is K and this is K1. Why am I doing this? Is to find the purpose of this is to find the internal resistance. To find internal resistance of a battery. So there is a battery here, a cell here. To find internal resistance of this, I should have an external resistor, because the relationship between internal resistance and external resistors, I just told you, is small r is equal to capital R into E by V minus 1. Didn't I derive this in the first place? Very, very important. You already know this. So therefore you have to have an external resistor. Okay. Now let's take this is the driver circuit or auxiliary circuit, and this is the secondary circuit, as you can see. And initially from a higher potential the current flows, and then at one particular length of the wire the current stops flowing, which shows that E would have dropped down to E1. E would have dropped down to E1. Actually, I'm not connected. I'm keeping initially. I'm keeping K1 open. Initially, I'm keeping K1 open. So only E1 is connected to the auxiliary circuit. The circuit has got just E1. Can you imagine just E1? So E drops down to E1, and for one particular length that I'm measuring, say let's call it as L1. That for initial length, when only E1 is connected, then you know E1 is proportional to L1, or E1 is equal to K into L1, where K is the potential gradient. Okay. Next, what I'm going to do is connect the external, close the key K1. Now, what happens? The external resistance comes into play, and so now what happens in the secondary circuit? It's like connecting a bulb to it. You know, it's equivalent to connecting a bulb to it. The internal resistance will show its head because the current starts flowing in the secondary circuit. In the secondary circuit, the current starts flowing in. And because here it's closed, so still you will have a current here, even though there's no current in the galvanometer. Within this circuit there will be a current, secondary circuit, at which time I'll have an internal resistance showing its head, and so then the E1 will drop down further, because you know V is equal to E1 minus IR, because when the current starts flowing in, you already know that this relationship when the current starts flowing in. So then E1 is not going to be E1, it's going to be V. It's going to become terminal potential difference, and that V is proportional to L2. So then therefore V is equal to K into L2. And simply take this formula and write small r is equal to capital R into E1 by V minus 1. Where in the case of small r is equal to capital R into E1 is KL1 by KL2, so L1 by L2 minus 1. Thus you know the two lengths, and you know the external resistance which you have connected is the resistance box actually. So with this you can find the internal resistance of the battery. So this completes the basic part of the lesson, very basic, okay. And next is, this is the first level of learning. As I said, if the level of learnings, or there are 3 levels of learning. First is to learn the basic level, then it's slowly enhance, and third is go in depth, okay. So I'm going to stop this video recording.